One more video lecture on graphs. In section 2.2 we'll be talking about histograms. Here's the definition. A histogram is a graph for quantitative data which uses bases of rectangles to represent classes of the variable and heights of rectangles to represent the corresponding frequencies of those classes. If you were to see a histogram on a website or in a book, you'd almost certainly call it a bar graph, and nobody could fault you for calling it a bar graph. But as we discussed in the last section, bar graphs are technically for categorical data, and histograms are for quantitative data. One thing that makes a histogram stand out from a bar graph is that the bars will actually be touching one another in a histogram. In a bar graph, we generally put a little bit of space between the bars. When we draw a histogram, we're drawing the graph of a grouped or ungrouped frequency table. So typically we find a frequency table first, and then we go through the procedure for finding the histogram, which I have on the next slide. First, you're going to draw two perpendicular axes. It would be awesome if that was just the word axes and we drew two axes, like for wood chopping, but that's the word axes, the plural of axis. So we draw two perpendicular axes, one vertical, one horizontal. One of them will be used to measure the value of the variable, and the other will be used to measure the frequencies of the classes. When I draw these, I tend to make the horizontal axis the one that measures the value of the variable, and then I let the vertical axis count the frequency of the class, but you could organize it the other way. Secondly, we're going to mark the class boundaries on the axis which measures the value of the variable. A class boundary is a technical word here. In our class, we're going to use the low end of each class as our class boundary, and then add one more class boundary on the right side of the graph. But you can do class boundaries using midpoints and all this other technical stuff. I'm not going to test you on any of that, so I'm not going to go into detail here. I should point out that I'm using this lower class boundary rule because that's the same rule that your calculator uses. I'm not going to go into the steps for finding a histogram with your calculator, but it can be done, and I'm going to use the exact same convention that your calculator does when I draw mine. The last step is to draw rectangles with heights corresponding to the frequencies of each class, just like you would in a bar graph. The height of the rectangle will tell you how many values fall in each class, at least if you're using the vertical axis to represent the frequencies. To make this go a little bit smoother, I'm recycling the examples from the frequency table section so that we don't have to go through the process of counting or anything like that. The first example was an ungrouped frequency distribution, scores on a quiz. Let's draw a histogram. So I'm going to draw two axes, a horizontal axis to measure the value of the variable. So I might label that below as score. And then a vertical axis to measure the frequency. I could just label that with an F, or I could put what that represents down this side. Like this represents the number of students, so I might write number of students. After drawing the axes, the next step is to use class boundaries on the horizontal axis, and that might cause you to wonder how we're going to do that when we don't have intervals here. Well, if we think about it in kind of a nerdy way, every score of 4 is technically between 4 and 5, not including 5. And every score of 5 would be between 5 and 6, not including 6, and so on, which seems like an unnecessarily nerdy way to think of it when you're looking at the table, but when you're drawing the graph, that's actually a good idea. The first class boundary is at 4, and the next class boundary is at 5, because the next class begins at 5. The third class boundary would be at 6. I put my label in the way, so I just pulled it down real quick. And then 7, and then 8, 9, 10. And the biggest score is 10, but if you think about what that last one would be, it would go from 10 to 11, not including 11. So I need to put a mark for 11, even though there wasn't a score for that. That's where the last rectangle is going to stop. Now I'm going to enumerate my frequency axis. I notice that these go as high as 6, so I need to at least have 6 tick marks. Of course, nobody's going to know what those represent unless I put some labels. And now I can draw in my rectangles. The first class, score of 4, has a frequency of 1. The second class, 5, has a frequency of 0, which means that we won't see a rectangle there at all. There's a rectangle that extends from 5 to 6 but with a height of 0. So it's not really a rectangle at all, it's a line segment. No height. And so you get this gap in the graph indicating that there were no scores in that range. There was one score of 6. There was one score of 7. And now you see that the rectangles butt up against one another. There were 3 8s. There were 6 9s. That was the most common. So we'll have the tallest rectangle. Let's all pretend that that was a rectangle. And then there were 3 10s. That last rectangle extends from 10 to 11. I know there weren't any scores of 11, but the convention that we're using is that the right endpoint is excluded. This is the exact same convention that your calculator uses. What a lot of textbooks will do is tell you to use the value on the left as the midpoint of your rectangle. So you'd have your rectangles kind of straddling these numbers. You'd have the first rectangle go from 3.5 to 4.5 and so on. And there's value in that too, but it's not the only way to do it. And since you guys are all using the TI calculator, which uses this left endpoint convention, I'm going to do the same in class. We get the same information from the finished histogram that we get from the finished table. But there's something more appealing about looking at a graph. It also takes less time to analyze for what we call the pattern of variability or the distribution. You guys are all clearly good at math if you've made it this far, so that's not difficult to do, but it's immediate when you look here. You can immediately see that the class with the tallest rectangle is the one that has the highest frequency. You can see that the data is kind of skewed, and there's much more of the data bunched up on the right side than on the left side. And again, we got that same thing from the table, but it's immediate in the graph. You can see it all at once without having to scan each individual row. Let's do the other example. I did this example with the number of views for a popular YouTuber. We had decided to use a class width of 10. And when you look at these numbers, again, you might say, well, I only see a class width of 9. Well, that's because the class width is measured from lower endpoint to lower endpoint, or from upper endpoint to upper endpoint. Or another way to get that class width is to realize that that first class really extends from 18 to 28, but not including 28, and there's that class width of 10. Then the next class takes over at 28 and goes up to, but not including 38, and so on, all the way down to the last class, which begins at 58 and actually extends up to, but not including 68. I know this upper bound was 67, but the class boundary is going to be 68, not including 68, at least with the convention that the calculator uses. I'm going to draw a histogram for this grouped frequency distribution. So 2 axes, one to measure the number of views in millions, and the other to measure the frequency. The frequency here is the number of videos with that many views. My first class boundary is 18, so I'm going to start with 18. Notice, by the way, that this isn't the point 0, 0. I don't have to start with this at 0 and find 18 somewhere over here. You probably want to put a little bit of space between the first lower class boundary and the corner there, but you don't need to put much. You don't need to think of it like this is the XY plane. The next class boundary would be 28 because that's where the next class begins. And then 38, 48, 58, and I need an endpoint for my last rectangle, so I have to go out to 68. That's why I took the time to write this last nerdy inequality notation, so I knew where to end. I see that my largest frequency is 11, so I need my axis to enumerate to 11. And while 11 isn't a very big number, just to show you that it's allowed, what I'm going to do this time is count by something other than 1. I'm only going to count by 2s, but I could count by 3s and still get a decent graph, but I'm going to count by 2s. So 2, 4, 6, 8, 10, 12. My first class has a frequency of 5. Halfway between 4 and 6. There's my first class. Next one has a frequency of 11. And then 4. 3, halfway between 4 and 2. I missed my spot there. And then 1. And again, we get a visual representation of the grouped frequency distribution. This histogram has the same drawback that this table has, which is that we don't actually know any of the values of the variable this time. When I look at this first rectangle that extends from 18 to 28, I can tell that there are 5 videos in that range, but I have no idea how many actual views each of those had. So we do have the same drawback that we have with any group frequency table. If we needed to know what the actual data was, the histogram wouldn't be the best choice. We'd probably want to use a stem plot instead. It would still group the data, but we'd be able to see what it is. But we get this nice visual representation. You can see that the graph is kind of mounded. And I keep talking about this shape. That's because we're going to be interested in what the shape is. And in particular, we're going to be interested in when the data comes out to a normal distribution. We'll get into this more formally later, but the normal distribution is a symmetric bell-shaped distribution. If we get a histogram where the data is kind of symmetrically placed and peaks in the center, we can kind of outline it with this bell shape. You can see the bell sitting there. We're going to learn later that when you know that a set of data is normally distributed, there are lots of nice properties that come for free just by knowing that it's normal. We'll be analyzing normal distributions quite a bit in this class. One way to determine that a set of data might be normally distributed is to first draw the histogram and see if you get this mounded symmetric shape, this bell-shaped distribution. If you get a shape like our previous example, where it's kind of skewed on one side, then we might infer that the data is not normally distributed from that. So again, I want to make sure expectations are clear. You don't need to really know how to draw a histogram. I'm not going to ask you to do it by hand. And I do want you to have a feel for how it's done. I want you to understand that these are the graphs of frequency tables for quantitative data, which means they're going to have similar restrictions, like you're going to want 5 to 20 classes, so you'll have 5 to 20 rectangles most of the time. And I also want you to know that we use these not only to look for things like the most common class, but also to look more generally at the shape, what we call the distribution. And certainly the most important distribution is the normal distribution, which is a bell-shaped distribution that we'll be studying later in the class. That's all I've got for you. If you have any questions, shoot me an email or see me in an office hour.